Okay, let's start. So I'm gonna talk mostly about internals, and this is going to be pretty much technical talk. So if you will not follow me and you will have any questions regarding any of these slides, technical questions, please free to stop me and ask them, okay, right away, because later on apparently you can forget them. So in this talk I'm gonna speak about most common .NET performance issues, which apply not just to the world of IDEs and desktop applications, but also to any kind of applications. And then I'm gonna apply these issues to the world of IDE, and then I'll tell you how this world, the IDEs for .NET, um, this world was evolving from time to time. So talking about .NET performance issues, I think there are mostly three kind of issues. Actually two, but I decided to make a third point. First thing is the busy UI thread, or if it is a server application, let's call it dispatcher thread, right? So for example, for desktop application, if your application freezes or laggy, anyhow, but this is the problem of user interaction thread, UI thread, user interface thread. The reason why UI thread is busy, there are a couple of reasons, bunch of reasons. It may be just some algorithmic error, right? And you're doing, I don't know, while loop in UI thread for minutes, maybe. Maybe it is a contention, thread contention, when UI thread is waiting on a lock to another thread to release this lock. Or it can be I/O or any other questions, other reasons. Another main reason is garbage collection. Garbage collection is very important, and I'll tell you later why, because it actually suspends all the threads, including UI thread again. And the third point, I would rather merge it to second one, but let's write it down here, is a high footprint, the high memory usage of application. Why is it important? Because if your application consumes a lot of memory in operating memory, then garbage collection will be triggered much more often, right? So yes, that's true. Of course, but right now we'll be talking mostly about full framework, .NET Core framework, not about Mono, because Mono world is totally different. So of course this depends of overall size of your available memory, right? But if you exceeded the size or close to this size, then you'll get some problems. So before going deep to examples, I just want to start with a very brief demo of how we diagnose these problems, okay? So what I'll do here, oh sorry, I'll do this. And I show you my remote desktop on Windows. And this is the tool I really love. It's called .trace timeline. So how many of you know about this tool, .trace? Okay, not all of you. So .trace is a .NET profiler made by us. We were developing this tool for more than 10 years. We started with a simple .trace that allows you to view the tree of your, like a normal profiler, the tree of a call stack. The timeline we introduced, I think 5 or 6 years ago, no, maybe even 4. It allows you to view the overall thread, like all the duties of from all of your threads within the timeline. So you will see that, okay, so here the main thread was busy for how many? Oh my god, for a minute. And then main thread apparently was, maybe was or maybe was not, waiting for these three guys, these three background threads, and then another background thread. So I understand what every thread was doing. And here, like for example, this is a typical case when the UI thread was busy. It was doing something. And with dot trace, you can make a custom selection and then return back. I'm sorry, the screen is too narrow and small. On the full screen, it's much easier to work with, but you will see the whole call stack for the selected region, for the selected thread. And I'll see, okay, I'll do something C++ related here. So here's the issue. It also shows me the contentions. So for example, if this thread was waiting for another one, it will show me, hey, it was waiting for this kind of lock, and this lock was consumed by another threads. Another thing it shows is garbage collection. You see this yellow indicator on top of this, and 6.9% indicated here. So this is garbage collection time. So 7% from all these 3 minutes, application was stopped, was not actually responding because of stop the world made by garbage collection. So it's just one reminder and clue for you how to investigate .NET performance issues. Of course, I cannot be objective here, but believe me, I was using, for example, YourKit for Java profiling. I was using other SkiTag memory profiler, other tools. This .trace timeline is saving your time. It's so convenient to use. Maybe not very, maybe not very tricky to find this, but I'll show you this. Okay, so here you can press filters, and filters, of course, any of these options will apply to the selected frame on the threads view. And I can, for example, I can view the CPU time in the call stack, or I can view memory allocations, and it will show, like here it shows that for this selected region, for main thread, it was allocated 18 gigs of memory, right? So it's quite a lot. Okay, back to my presentation. Okay. So why we should care about garbage collection? Because as I said, garbage collection makes stop the world anyways. It will stop all the threads, including the UI thread. Easy conclusion. The more objects you allocate in your application, more often you will trigger garbage collection to stop the world and freeze your application for a while. So as you may know, there are 3 kinds of garbage collections in .NET. Garbage collection 0, GC1, and GC2. How many of you know about this generation concept? Yeah, so basically there are 3 generations. All your memory is divided into 3 generations. Generation 0, Generation 1, and Generation 2. The approach that Microsoft uses here is that, like, most often you have lots of objects with a short lifetime, and they have to be consumed frequently. And some objects, apparently, these objects will live in your application much longer, and we don't need to collect and to walk through this complicated graph too often, because apparently they will live longer. And because of this, garbage collection works in 3 stages. GC0, which works really frequently and really fast, but it works only on generation 0. If some objects for garbage collection 0, for GC 0, some objects are reachable from roots, so they're actually used, they will be moved to another generation, so on and so far. So with this approach, for example, garbage collection 2 occurs much rarely, but it's also much heavier because you have to walk through really large generation 2. When we talk about the average time for these three guys, Microsoft promises us that garbage collection 0 should work for actually microseconds, not milliseconds, but anyways, it's less than 1 millisecond. Garbage collection 1, we measured it, works approximately about 3-5 milliseconds for 1 gig application, desktop application like Rider. The important thing here is that garbage collection 2 can work for seconds. And again, for these seconds, your application will be freezed. Okay, this is important. So when we, for example, the same screenshot taken from timeline tool I've just shown you, here we see that although the UI thread here is not busy, is not pretty busy, here we see, you see these tiny yellow spots. It's apparently garbage GC0, GC1, and these thick ones are obviously GC2. And during this period, your application is freezed, and it is also shown here in timeline, which has an indication of UI thread freeze with this purple line. What is also important to understand is that if you have a multi-threaded application that uses multiple threads a lot, you'll gain even more problems with garbage collection. Why? And here will be a tricky example. So it's called middle age crisis of objects in this hard.NET world. Yeah. So for example, you have a single thread application, and in this application, let's say in for each loop you allocate, I don't know, thousands of objects. These objects are temporal, they are local variables, they have to be collected in GC0. And yeah, in a single threaded application, here it's thread number 2, I will allocate all these objects. Maybe later on the threshold for the garbage collection to occur will be reached, for example 4 megabytes. Garbage collection 0 will be triggered, and it will allocate all this all these local variables which are no longer needed, right? If you have another thread number 1, the following happens. So I allocate in thread number 2, as I said, allocate these local variables, some, let's say, temporal local memory, and then all of a sudden, because thread number 1 also allocate its memory, this threshold for 4 megabytes will be reached during this loop, right? The time before this loop will end. And because of this, at this point, these objects on thread number 2, which supposed to be collected by GC0, will not be collected because garbage collection 0 occurs, and at that moment, these objects will be reachable from roots. They will be used. So these objects allocated on thread number 2 will be, let's say, unfairly moved to next generation. Generation 1 and generation 2. And because of that, generation 2 might be even bigger, and garbage collection 2 might occur more often. Okay? Okay. So, yeah. When we, how to fight with this? What can we do if we notice that our application is being freezed because of garbage collection? Of course, allocate less objects, but sometimes objects are allocated implicitly even without this new keyword, right? How? C# is a great language. Of course, Kotlin is better, but it's number one. Sorry. I used to say that C# is number one before I tried Kotlin. So anyways, C# is a great language. It evolves fast and it gives us a lot of features, but we have to pay for this syntax sugar, and we have to pay for this awesome language. How? For example, we write a simple lambda here and pass it as it's shown here. Pass local variable s, right? And this local variable with the name s will be captured. It's some kind of closure. So this is the code we see. There is no new keywords here, right? But if you will dig into IL code after compilation, you will see what actually be generated. Not to dig into IL code, not to make this talk too hardcore. Let's do another trick. Let's compile it and decompile it with .peek and press and toggle this button, show compiler generated code. And we'll do this, we'll see that compiler actually generated new capturing class, closure class. Actually, it is the only way how this would work. Does it make sense? It just allocates how many? 12 bytes? No, but if it's inside a huge for each loop for million iterations, it will make sense, right? Another example is params keyword. With this keyword you can, as you know, you can pass as many params as you want. And of course, right here I'm not passing anything, I'm not creating any new object, right? If we'll do the trick and repeat our exercise, we'll see in .peek with the compiler generated code, the compiler always set a new array in this situation. I will not tell you about all of these situations, all of this compiler syntax sugar. We'll just run through a couple of others, but I just want you to understand that if you see a perfect and clean code, it's not so perfect inside. So for your code to be clean and readable, sometimes you have to pay with performance penalty. Another performance example is yield keyword. It's pretty common example. I just iterate on yield. But with yield keyword, compiler generates even bigger capturing class, as it's shown here, which is even heavier than I shown you before. So if you're doing yield inside yield for million of times, you probably will get these garbage collection problems. Okay. Another problem we've noticed, I think it was 6 or maybe even 7 years ago. So in ReSharper we have a concept called lifetime. Lifetime actually encapsulates the lifetime of an object. Wow. So it has an API that has an action. First action will be executed right away, the beginning of this lifetime, and the second action will be executed when this lifetime is going to be terminated. And for example, this is a lifetime. In this example, my lifetime encapsulates a long-term lifetime. For example, lifetime for solution, right? And we were thinking that compiler will generate 2 capturing classes here, as I shown you before, right? But it turns out that it generates only 1 generating class. Why does it matter? It matters because the first S1 local variable will be captured till the end of your, let's say, application, till my lifetime will be terminated. So this memory will be held. Okay. These examples just to maybe to ruin some naive vision from some users which do not understand some things. Just dig in a while and you'll see how it works internally. How can we fix this? One of the easiest fix is of course moving redundant allocations in if conditions. So for example, in this case I capture local variable e, but I can move it inside if closure, and if I move it inside, e will be captured much more rarely, and in this case I will not allocate a bunch of memory. Another thing we have to consider is garbage collection health. So it occurs, as I said, when garbage collection, when your application has a huge footprint and consumes a lot of memory, and application is allowed to have limited size of memory. Or for example, you have 32 bits application like Visual Studio. So for example, we have Visual Studio that operates with realistically 2 gigabytes of memory. So if your application will consume 1.5 gigs, the garbage collection will occurs much more often, because it say, hey, you have, like, you're very close to the threshold. Let's collect, and if Visual Studio consumes more than 1.5 gigs, kill it. It won't work. Right, garbage collection occurs when application holds a huge amount of memory. We call it footprint. In this case, garbage collection is triggered quite often, as I said, and if you gain these problems, you have to think about how optimized are your data structures. Do you really need all this memory in your operating system? How can we improve on this? First, we need to know about, again, internals, and let's talk about large object heap. How many of you know about large object heap in .NET? Okay, so the funny stuff about large object heap log is that the overall experience can be described when you translate this word in 3 languages. So in English it would be, very straightforward, large object heap for large objects. In German it will be like a whole log. Yeah? Wissen Sie? And in Russian, log actually is a swear word with mean like asshole, like this, like idiot. So the thing is that if your objects are large and they are unintentionally went to log to this space, your memory will have a lot of holes. It will be very fragmented. Now, speaking more officially, large object heap is a special heap for large objects which are larger than 82 kilobytes, I guess. And what is interesting about this large object heap is that it just grows. If you're not compacted manually, it will be just growing. And as you can see via this, actually another awesome tool, .memory, which can show you the heaps, the heap chunks, you see that this large object heap has a bunch of white spaces there. So large object heap, where all these large objects are located, is very fragmented. There are a lot of holes there, and because of that, it consumes much more memory that you actually that you actually need for your objects. And because of that, your footprint might grow much more than you would expect to. So, for example, with this tool, with dot memory, you can understand this. You can click on the blue line. You can understand what object is located here. Why do you allocate such large objects in your application cycle? And maybe do not allocate these objects. Or what can you do? You can do chunks, because actually which are, can you tell me the objects which are greater than 82 kilobytes? Arrays, right. These are arrays. So instead of making a single pure array, we can make a chunk array with 2 dimensions. And with this approach, these chunks will not go to a large object heap. They will go to a normal, apparently generation 2, and they will be collected. In starting from .NET Framework 4.5, you can manually compact large object heap with the following code. It's not very complicated. You can Google it or Stack Overflow it. It's just pretty simple and it works. But just be aware that during this compaction, again, your application will be freezed. We can do this in Rider because I'll tell you this later. Rider's backend is separated from the front end, and these freeze will not affect the smoothness of your typing. Another thing you can do with reducing a footprint is storing your memory, your objects, actually on a disk. How many of you have heard about LevelDB, for example? So LevelDB is a key value storage made by Google. There are a bunch of others, key level databases. And what it offers you is an API to say, okay, here's my dictionary, and I want to persist this dictionary on a disk. For example, this green is the whole memory I have right now, and I have a lot of memory. But I use at one moment not all of these, but maybe, I don't know, 5%. So what you can do is to build a last recently used cache, like our own modern processors work, which, how does it work? It stores the most frequently used objects in operating systems, and therefore access to this object will be fast. And if you will ask for another objects which are not here in operating systems, or operating memory, sorry, it will go to the disk, get this object from disk, place it in this cache again. So with this approach, we've reduced our footprint dramatically. Okay. Let's continue with UI smoothness. And before I'll show you example, just a couple of words about ReSharper memory management. And at this point, we are slowly starting to move from common .NET performance scenarios to the world of IDEs. Okay. So ReSharper content model is something all the features operate with. For example, we have, as I said, thousands of features: find usages, code completion, navigate, refactoring, all this stuff. And these features can be triggered and they can perform on pull thread again, right? Not to make UI thread so busy. They want to operate with consistent data structures. So for example, if I calculate find usages in a background, right? In a background, and I still allow the user to type. If during this process I type something, and this typing will affect the result of my find usages that is being run on the background, right? What I have to do, I have to restart or cancel it. I have to understand that find usages in the background thread are working on invalid data right now. Okay, so to do this, how can you do this? There are two ways actually. First way is pretty simple, is to acquire reader and writer lock. So in my example about find usages, it works like the following. Find usages acquires the read lock, it reads the data. Find usages doesn't need to modify the data. And typing on UI thread needs to modify this data, and therefore UI thread acquires a write lock. Okay? So in this content model, lots of stuff is placed. Project model, this is about your assemblies, projects, files, PSI, so-called syntax trees, symbols, caches, some indices. Indexes is spelled incorrectly. Yeah, so, and all operations with this model should be done with a read or write lock. Now here we have a problem then. For example, I have a pull thread, not UI thread, pull thread, and in this pull thread, as I said, for example, I calculate all the usages. To calculate all these usages, because I told you earlier, I gotta acquire read lock, right? So here in this pull thread, I have read lock, and then all of a sudden, boom, I'm started to type something in my application. Thing I need to do in my code, in my background code, is frequently check for interrupt and check if somebody somebody wants to acquire write lock, and if it does, then I have to cancel my background activity and let these guys to obtain write lock as soon as possible. So if the background code has all these checks for interrupt, we are fine. And if you, for example, in ReSharper, if you launch the background activity, the typing will be smooth because, for example, I press a key, let's say 30 milliseconds passed, another check for interrupt on the background triggered, it allowed me to acquire write lock, and after, let's say, 50 milliseconds, I got the write lock. 50 milliseconds is fast, you will not notice that. But if your background code is not interruptible and acquires read lock, you got into problem, and your UI thread might be freezed. Okay, so these were major problems we were struggling with in ReSharper. And most of these problems I think we've resolved even in ReSharper. However, there are a bunch of Visual Studio problems. So which are these? First problem is that it is a 32-bits application, even today in 2018. And do you know why? Sorry? No? Okay. I'll tell you why. Because there are too much dirty C++ hacks over there. even some interop modules, interfaces contain int, not int ptr, if you know what I mean, right? So will not be easily ported. Although maybe they will change this, but they will definitely make a lot of effort to rewrite this. Another reason why Visual Studio sometimes is very laggy is because of STA COM. How many of you have heard about COM interfaces, single thread apartment, multi-thread apartment? Okay. So COM is a legacy, very old technology. Sorry? Voodoo Magic, yes, technology. So you have something written native, but it's exposed to your managed world via COM interop. And COM objects, they can be declared as MTA and STA. So STA, it is a single thread apartment contract. And STA means that this COM object can be accessed only from UI thread. Yes, another problem with COM objects is that it's very hard to see what's going on under these COM interfaces because it is a native code. Why do you think they couldn't do all these COM objects MTA initially? I'll tell you why. Because the core of Visual Studio was written in 1998 when we just didn't have this kind of processors. Nobody really cared about this. They started to care about this maybe in 2003-04, and it was too late. Too many C++ code. So another problem with Visual Studio Performance is memory pressure caused by Roslyn and ReSharper being installed, because of course ReSharper consumes a lot of memory. Again, because we have to hold all this content model in a memory. And of course we're improving in this and improve a lot, and with where was it? Yeah, with this technique moved a lot of these objects to the disk, but still. Okay, any questions so far? You mean for ReSharper? For Rider we don't have such a problem. For Rider we don't. That's why we introduced Rider, not to have these problems. So, and then came Roslyn. And Roslyn actually is a very beautiful idea, I have to say, although we compete with Roslyn, based on some scientific work by Neil Gafter. And the key principles of Roslyn are that it is immutable, and I'll show you exactly what do I mean when I say immutable. It is lazy and it's thread safe. So, for example, you have a file, C# file. All IDEs build a syntax tree on top of this file, right? Syntax tree. And when you modify this file, what does ReSharper is it modifies this tree in the memory. And this tree, again, as I shown you, is the part of this content model, right? What does Roslyn is exactly different, is absolutely different. When I modify this file in Roslyn, instead of modifying this structure and acquiring for some sort of logs, I just invalidate the affected nodes and then reconstruct the new snapshot, the new part of the model from scratch, although they re-implement as much as they can. For example, I have deleted a method inside a class, right? So here will be the method in my AST3 tree. And what I'm gonna do, I'm gonna just change. Of course, I have to replace this stuff with a new copy of based on a new text I've entered there. And I have to just replace the links just in these two guys. The rest will remain the same. This approach they call thread and green tree, and it's very beautiful idea, and it solves the question of multi-threading. In Roslyn, I don't have to care about these read or write locks, about these interrupts, right? How does it work? In Roslyn, when I have a UI thread and a pull thread, and again, my find usages feature is working in the background thread, and then all of a sudden I started to type. What happens here is that I changed the tree to a new version, and here I just have to interrupt and say, hey, the new version of a tree occurred in UI thread. No need to continue the execution this in the background thread. That's it. So because of that, maybe people started to write the analyzers on Roslyn API, not on ours. We solve it with supporting both. But even with this beautiful approach, Roslyn guys, they faced another major problems, which are the binding engine. The engine that it's gonna be very hard, but just in brief, binding engine is an engine that resolves the symbols. Resolve the symbols, it means like if you write my variable dot foo, and foo returns a type, let's say type called Roslyn, I have to bind to resolve that this specific expression resolves to type that's called Roslyn, for example. This binding engine is very tricky for CSharp because there is overload resolution, for example. There are, let's say, 5 foo methods with different overloads. They are generic, all this stuff. So it's very complicated engine, and this engine works like it doesn't know about whether it was asked from out of date thread or not. It just gives you all the results, consumes CPU and allocates memory. So this engine is not interruptible, and they don't know how to do it interruptible. Or maybe they know, but it's very tricky. Because of this immutability, because of this beautiful idea, they have to allocate even more objects because they have to build new projects from scratch, even though they try to reuse as much as they can. And this produces even more heavy memory traffic. And the overall high footprint for large solutions, just for Roslyn, is not low. Just checked it on a ReSharper solution, of course with ReSharper turned off. So pure Roslyn, even without I just open the solution, it consumes 1 GB of memory. So it's really hard to work on our solution in Visual Studio, even with ReSharper turned off. Then a bit of politics, like, you know. So, like maybe 3 years ago, Microsoft started to step on our toes with this. And I said that I told these reasons to you in my introduction speech. So we decided to make Rider, which will, and with Rider we'll be able to open huge solutions without all these issues. And we introduced Rider. What is Rider? Is absolutely new IDE based on new crazy technology. What we have here is we have a backend as a standalone process. This is ReSharper taken out of Visual Studio. And this process we will support the code, so this process can be run on Mono as well, right? So when you run Rider outside of Windows, Rider runs on Mono outside of Windows. We're thinking about moving this to .NET Core runtime, but I don't know when, maybe this year. And as a front end, we took IntelliJ platform, obviously, because it is powerful, it is our front end, and we can reuse it is cross-platform, and we can reuse all these features from IntelliJ platform. But of course here, this front end, as a process, has nothing to do with these complicated tasks like caching, syntax trees, all this, right? So with this approach, backend's garbage collection still occurs, and we still can work on this, but this garbage collection won't affect the smoothness of your front end. It will suspend the UI thread of a backend, right, of the backend, but you still typing in a front end. Of course, backend is 64-bit process. The most of communication between front end and backend are asynchronous. So front end is rarely waits for backend synchronously. We still have some kind of these awaits, and we'll get rid of them hopefully this year. It's kind of tricky because to get rid from all of this, we gotta write something like Google Docs, when a bunch of people can simultaneously modify the document. What I'm talking about is that what kind of these synchronous operations are. Type assist, for example. When you press enter in Rider, you auto format your code according to your code style, right? And as I said, front end cannot do this because front end is lightweight, so backend should do this. But right now we are waiting for backend to do this because let's say garbage collection will occur suddenly and it will last 10 seconds, right? So let's say we backend is performing this complicated enter typing assist. Garbage collection occurred here, and so we are waiting for 10 seconds. But if we would need to do this asynchronously, and in this scenario we'll continue typing, then boom, after 10 seconds, this formatting change came back to front end. What we have to do, we have to revert my front end changes, apply backend, and apply backend changes, and apply my reverted changes again on top of backend one. This is what you see when you simultaneously modify the code in Google Docs. Even some people modify the same piece of text in Google Docs, but still you see it consistently. Okay, so but anyways, even with these synchronous operations, these operations are very fast, so it's very hard to find any type of assist that will last like more than, I don't know. So the round trip from front end to back end and then from back end to front end is about 1 millisecond. Just 1 millisecond. Noticeable delay for you when you're typing starts from 150. Yes, and with this approach we gain lots of cool features from IntelliJ. For example, Matthias shown you today version control support, or HTML, REST client. We get these features for free. IntelliJ evolves and we gain this feature. The backend and the front end are bound with our own protocol. Our own protocol is something really interesting. It can bind C# to C#, C# to Kotlin, any kind of these languages, C#, Kotlin, or Java and JavaScript. And maybe more will come in the future. Our protocol, what is important, is stateful. When I say stateful, what do I mean? And I think I showed the code you in the demo a little bit later. Now I'll show you in my hands. When we communicate, as I said, front end communicates with backend and vice versa. They can communicate in a stateless manner. For example, throw a signal, hey backend, calculate find usages for me. Backend calculates all the usages and responds, hey, here you go, here are a bunch of usages. We can do this. But at the same time, we can do it in a stateful manner. So we will say, for example, not hey backend, we have something for you, but here is the protocol model that will be synchronized across these two parties. For example, this is the caret model, the model of the caret that is in your editor. So instead of sending these signals, we just say on the front end, caret model, modify the caret model. We don't care about the rest. Protocol will do it for you. It will synchronize these changes on the front end to backend, and the backend in a reactive manner, like I notify property change, will get these changes and apply this to the backend content model, and vice versa. I'll show you the code of this rocket science technology a bit later. It is very fast. Internally, it works via sockets, local sockets, and we were never struggling with the performance of protocol. No, we were 2 times, and we solve it with interning. So even sending huge amount of data will be done like this in maybe 100 milliseconds. And we are planning to open source this protocol soon. With this protocol, we're not binding just front end and back end. We are binding everything together. When we are debugging, we have a separate process called debugger worker, which is of course bound with front end to show what has it evaluated. And it is bound with backend because it needs some of the language services from backend, from ReSharper. For example, to make a resolution, overload resolution. Our project model and build are also done in a separate processes, because to load your solution correctly, you have to use the correct runtime. So for example, if you have .NET Core solution, you have to load the solution, the project model for this solution projects within the runtime, .NET Core runtime. The same with build. As Matthias shown you, WPF preview also works separately, even outside of backend, and transfers the rendered WPF code to the backend, also synchronously. This Roslyn stuff we showed you today, it is also a separate process which hosts Roslyn logic inside, does all the Roslyn analyzers, and then return back to backend. And then backend, all these results can be applied to backend solution-wide analysis mechanism. Because of this, we got all this Roslyn inspection solution-wide, and Visual Studio cannot do this. And even more exciting stuff, with this protocol, we started to communicate with external tools. So to show this, let's start a final demo. Record. Okay, so here's the demo. Here's my Rider running on my Mac, and here's Unity Editor. Unity Editor is the most popular game engine right now. In this editor, you can design your games, design just everything, 3D objects, music, audio, just everything. The cool feature of Unity 3D, why it became so popular, is you just place all the crap you have in just one folder, trigger, build and run, and it will compile everything. So you just place jars, DLLs, CSharp files you bought in the asset store, all the stuff, build and it will work. But still, so basically you can write a game even without any line of code in C#, Unity Editor. But for good games, you have to write your logic on C#. And what we built right now with this protocol, just an example. So I have a Rider running right now, I have Unity running simultaneously, and these two guys are bound together with our own with this protocol. And what it allows us, for example, there are some it's called unity tests, and these tests cannot be run with NUnit. These tests can be run only within Unity Editor, because only Unity Editor knows about all these game scenes, all these objects, etc. So with Rider, we can still do this. Watch this. Place run. You see here, Unity editor is actually running this test right now and passing back all the results back to Rider. And I see, and these tests are performed in Unity editor absolutely correctly. Or for example, here we have these buttons, and these buttons in Rider, they correspond with the same button in Unity editor. So if I'll trigger play mode here from Rider, boom, voila, I just started in Unity editor, and a bunch of other features. So this approach gives us very good, amazing opportunity to integrate with external tools very tightly. And to finish my presentation, just to show you a piece of code. So this is Kotlin, and this is Kotlin DSL. Quite easy to read, isn't it? So here is the model I described to you. The stateful model that will be synchronized between two parties. Either it's front end or back end, or if you want from back end to Unity editor. And when I change these items, this data, it will be automatically reflected. It will be automatically synchronized on the other side. So here I say, for example, and this is a real code that works in Rider, I say that text control model consists of selection, viewport, the thing you see when you scroll, right? Tab size, margin, all this stuff, other related stuff. When I press go to declaration, I see that text control selection consists of selection anchor and active position. Then what happens is that when our generator generates Java code for front end, Kotlin code for front end, sorry, and C# code for back end, right? Because back end is ReSharper written on C#, front end is IntelliJ written on Kotlin. And these parties, front end operates with generated Kotlin code, and backend operates with generated C# code. And they just consumes this, like iNotify property change, in a reactive manner. Okay, that's it. That was my presentation. Very hardcore and internal. I hope for some of you it will help. And yeah, if you have any questions, please ask. I will be happy to answer them.